So this is ELC 131, and I want to present some information on three-phase power. Now, if you look up, you'll see a power pole. So I can draw a little power pole here, and the top of this power pole, you see a spreader. And let's draw another little power pole over here. It's a happy little power pole. And this one's got a spreader also. And there we go. And let's draw one more. It's another happy little power pole. There we go. One more. There we go. Some happy little power poles. And you'll notice that on these power poles, there's actually three wires that connect these power poles, that connect together, suspended by these poles and the spreaders. And I'm going to draw these in three different colors, just because, of course, it's more fun. There'll be another wire here, goes and connects to right here, and goes and connects to right here, and goes off in the distance. Then there'll be a third wire here, connect to this one, and connect to this one, and connect to this one, and then goes off in the distance. And then there'll actually be a fourth wire here that connects to a point lower on the pole. There we go. And these are actually suspended with insulators off of the pole, but I won't try to sketch those in here. Now, these three conductors right here are our hot conductors. They sometimes referred to as the line voltages. But this is our three-phase power. We'll use this symbol for phase. And then this conductor right here is the neutral. And the neutral, of course, is connected to go down to a wire that connects to a rod that's driven in the ground. So the neutral is grounded. And we'll talk about what the three-phase power is here in just a few minutes. But the neutral is really the return path for current to go back to the substation, where it goes back to the nuclear, to the power plant, the power generation point. But this neutral is connected to ground at the power pole. It can sometimes also be connected to the guy wire that holds the pole in place. Now, what we do for our homes, and let's draw a little home here. There we go. It's a lovely little home. It's a nice home. It's a small home. Put a little window on the front door, a doorknob, and then we'll put a little window here so we can see out. And oh gosh, let's go ahead and put a little chimney here too, just because we can. So coming into our home, what they do is at the transformer, the big gray can that sits on the side of the power pole, they connect from one of the hot lines, one of the line voltages goes into the transformer along with the neutral. And of course, this is simply the primary of a transformer right here. And then the secondary of the transformer connects to our house or our home as shown, but we also have a connection from the neutral over here to the output of the transformer. So we actually have 3 wires coming into our home. So coming into our home is a single phase of power. Now, the voltages on these lines, the hot lines, could be, for example, 7.2 kV. And of course, coming into our home, so what we see inside this transformer is let's go right here. Okay, so our primary voltage is our 7.2 kV, and our secondary voltage, oh, I draw too many humps there. It should only be 1, 2, 3, 4 humps for a transformer. Our secondary is going to provide us from this point to this point 240 volts. Now the neutral again connects back to the center tap of the transformer. So therefore this is the secondary voltage. From here to here, we've got 120 volts, and from here to here, we've got 120 volts. And of course, when we get to our house, this neutral point right here connects to another rod that's connected into the ground. So at our home, the neutral is grounded also. And this is just really the reason we do that is because if we don't ground at this point, understand that when current flows back to the substation along the neutral line, we could have a voltage difference exist along this neutral wire, which would actually raise this neutral at some voltage above ground. And we want to make sure that the neutral is connected to ground. So if you touch the neutral and ground at the same time, there won't be a shock hazard present. Now, even though we have coming into our homes 2 120 volt supplies and of course a 240 volt supply, understand that these are in phase with one another. Because if we look at the 120 volts, it's going to look like this as far as polarity goes. We look at the other 120 volts, it's going to have the same polarity. In other words, when it's positive to negative here for the 240, our 240, of course, is just going to be a bigger voltage. But when it's positive to negative from here to here, then of course this 120 volts will be positive to negative. This 120 volts will be positive to negative also. So we only have a single phase of power coming in. We really have 2 120 volt sources coming out, but they are in phase with each other. So we call this single phase. Now, for our commercial and industrial facilities, let's draw a big commercial facility. It looks like a box. What they do is they would have a transformer here. And of course, this transformer would take all 3 of these wires. All 3 of the wires go into the transformer. Oh, I forgot to change colors. That'll be all right. Along with the neutral. And then the neutral connects over here, and then we'll have 3 conductors. Let's use a different color here. 3 conductors leaving the transformer to go into our facility, along with the neutral goes in here also. So we've got this 3 phases of power going into our commercial/industrial facility, where our homes only have one single phase of power. Now, what does three-phase power mean? Well, it means that we have three different sine waves provided. And these phases are called A, B, and C. And let's just look at what this will look like. We would have one phase here. And let's see, this is my negative peak point. Good, I'm doing good so far. And right here, and oops, that slipped a little bit. And let's do one more cycle. Oops, too low. I missed my mark. There we go. So this would be phase A. And then we would have another phase, which would be 120 degrees different than phase A. So this phase would have, let's see, that's 30, 60, 90, 120 is right here. And let's see, this would have a peak point, 30, 60, 90, 120. My peak point would be right here. So phase B will actually differ from phase A by 120 degrees. So let's see, this is 1, 2, 3. This is my zero crossing here. And 1, 2, 3. This is my negative peak point here. And let's see, 1, 2, 3. This is my zero crossing. And 1, 2, 3. This is my peak point. And 1, 2, 3. This is my zero crossing. Okay, so let's see, 1, 2, 3. This will be my peak point here. There we go. So there's phase B. And 1, 2, 3. This will be my peak. And 1, 2, 3. This will be my zero crossing. I'm getting tired. Now, there'll be a third phase, phase C, which differs from phase B by 120 degrees. So 1, 2, 3, 4. This is going to be 1, 2, 3. This is going to be phase C. Let's see, 1, 2, 3. And like this. So notice we've got three sine waves. They're all 120 degrees apart. Of course, this point right here being 90 degrees, and of course this point here being 180 degrees. So this would be my 120 degree point right here. So all three of these excuse me, sinusoidal waveforms differ by 120 degrees. This is what we mean by three-phase power. Now, we look at what's coming into our facility. These three phases can either be 120 volts, or they could be 277 volts. Those are two voltage levels that are common for our facilities. There's other ones that the list really goes on and on depending upon what we need. Now, as you saw, it's somewhat difficult and perhaps even a little bit confusing to think about what's going on with these three phases of power by sketching out the sine waves. So what we typically do is represent these three phases of power using a vector diagram. And we've seen this before when we illustrate voltage and current in RC, RL, and RLC circuits. So we've got one phase, that's phase A, that is right here, and we'll say that VA is 120 volts at an angle of 0 degrees. And I do that because phase A starts here at 0 volts. Now, where is phase B going to be? Phase B is going to be right here. So this will be phase B. And let's say this is 120 volts at an angle of 120 degrees. And of course, phase C is going to be where? Phase C is going to be down here. VC is 120 volts at 240 degrees. So it's really much easier mathematically to represent these three phases of electricity using a vector diagram than it is to try to sketch out these individual sine waves, as we saw earlier. Phase C feels kind of left out here. Let's finish him up. There we go. There we go. And of course, phase B, he's feeling left out too. Let's bring him on. There we go. That's much better. Okay. Any questions? Now, when this three phases of power comes into our facility, they have two configurations can exist. One is called a Y, and one is called a delta. We'll look at the delta in just a second. Well, we can look at it right here. How about that? So they call it a Y because when we draw this out, here is phase A, and of course there's going to be some impedance. We'll call this ZA, and here's going to be phase B, and of course his impedance ZB. Even though I draw these with a resistor schematic symbol, we have to think of these as an impedance in that they have some magnitude and phase angle, as we always have with AC systems. And of course down here is VC and the impedance ZC. Now this point right here is connected to our neutral, which will kind of symbolize with the ground symbol here. So phase A, phase B, and phase C all supply 120 volts for our example. 120 volts to their respective impedances with respect to ground or the neutral. Now, one thing is important when we start designing our Y system is that we need to have ZA at some angle. We'll call that theta sub A, we need to have that approximately equal to the impedance of B, and again, that'll be at some angle, theta B, which is approximately equal to ZC at some angle, theta sub C. We need to match these impedances as close to possible. And we do this for the reason to reduce the neutral current. And I want to go back to my previous drawing for just 1 second here. And there we go. So we'll pick out a point in space here, or in time, I should say, not in time, but pick out a point in time. Let's pick this point out right here. Now, if we look at voltage A, voltage B, and voltage C at this particular point in time, understand that VA at this instant, the voltage of phase A is at its positive maximum. The voltage of phase B and phase C are both negative. So what would be happening with our Y system is that at that particular point in time, we'd have a lot of current flowing this way. We'd have a smaller amount of current flowing this way and a smaller amount of current flowing this way because VA was at its positive peak. VB and VC were at some negative value, less than peak. But if ZA equals ZB equals ZC, both in magnitude and phase, then this neutral current will be 0 amps. So it's important in the design of our Y system, again, to try to match these impedances, ZA, ZB, and ZC, not only in magnitude, but in phase angle to reduce the neutral current because the larger the current, the larger the cable has to be. So we want to minimize, if possible, the size of the neutral. Now, our other configuration is called a delta. And here we've got our voltage VA. And down here, I've got my voltage VB. And over here, I've got my voltage VC. Now, existing between VA and VB, we'll call this Z1, impedance 1. And between B and C, we have some impedance. I'll call this Z2. And here some third impedance. We'll call this ZC. So with the delta system, we don't utilize the neutral. The voltage difference is the voltage between point A or VA and VB, between VB and VC, and of course VC and VA. That was 3 there. Sorry, I wrote a C. I meant to write a Z3. Sorry, messing my paper all up. Now, why do we do this? Well, one of the simplest reasons is that we can construct more efficient motors by applying 3 phases of electrical energy to a motor. We can reduce the amount of windings that we have in the motor. We can have a motor that turns with higher torque and less wire losses in the motor. So this is the biggest reason that we make use of 3-phase delta systems is by applying this to a motor. Again, I can have more efficient motors. Now, the question is, we know that with the Y system, from A to ground, I've got 120 volts. From B to ground, I've got 120 volts. Let's put an AC there. And from C to ground, I've got 120 volts. So the question is, what is the difference from phase A to phase B? What's the difference between phase B and phase C? And what's the difference between phase C and phase A? So again, what I'm going to do is I'm going to look at my vector diagram. 1, 2, 3, 4, 5. And here is phase A. It's again 120 volts at 0 degrees. And here is phase B, which is 120 volts at 120 degrees. And the question is, or the answer to this question is, what's the length of the line that exists from phase B to phase A? What's the length of that line? Well, in order to determine the length of that line, we've got to use a little trigonometry. And the first thing, well, let's start here. I know that the length of this line from here to here is 120 volts. So the question is, what's the length of this line from here to here? Well, to determine that, we go back and look at our trig identities, and it says the cosine of theta equals the adjacent side over the hypotenuse. And what we're trying to figure out is this length right here, which is the adjacent side. So we know that if we take the cosine of 120 degrees times the hypotenuse, okay, and the hypotenuse is 120 volts, then this will give us the adjacent side, and that adjacent side is, I thought I had that written down. Oh, the adjacent side equals negative 60. So I know the distance from the origin here to that point on the x-axis is 60 volts. Now I've also got to find out where this intersects up here on the y-axis. What is this length right there? So again, we know that sine of theta equals the opposite over the hypotenuse. So the opposite side will be equal to the sine of 120 degrees times the hypotenuse, which is 120 volts, which gives us 104. So I know this length right here is 104 units. Okay, so now I have this new right triangle, Okay, and that's this right triangle here with this side, and this side. And I know this side is 104 units. I know this side is 180 units. That's the sum of the 60 and the 120. So I can find the length of the hypotenuse. Of course, the hypotenuse, h, will be the square root of 104 squared plus 180 squared, which gives us a line length of 208. So the voltage difference between phase A and phase B is 208 volts. There is no angle associated with that, since there is no reference point. And of course, the voltage from B to C would be 208. The voltage from C to A would be 208. So it's quite common in our commercial facilities, such as Wake Tech. If you look at one of the panels in one of the labs, you'll see it's labeled 120-208. As this example shows, we can have a 100-208 volt system. Also, in some of the labs, some of the buildings on campus, we'll see a 277/408 system. Here we go. I was going to say something else and I forgot what it was. Oh, I know what it was. That when the easy way to calculate this, of course, is that to change the single phase voltage to a delta voltage, we simply multiply times the square root of 3. And I won't go into the math involved in doing that. But for example, if we take 120 volts times the square root of 3, we end up with approximately 208 volts. So you don't have to remember or do all this trigonometry that we show here, or I showed here. If you can simply remember the square root of 3 is our multiplication factor to convert the single phase voltages, the Y voltages, to the delta voltages.